The last thing I want to talk about triangles right now is about the relationship of the lengths of the three sides. So here's a natural question to ask. Well, can you make a triangle out of any three lengths? So let's say if we have lengths, I don't know, I'm just making these up. So here are three lengths of line segment. Pause the video, see if you can think about this problem. Can you make a triangle with these three lengths, or any three lengths? Try and convince yourself of what you think the answer will be. Try it a whole bunch, draw a bunch of different line segments of different lengths, and see if you can make a triangle out of those, and then we'll talk about it. Okay, now that we're back, I'm going to color these line segments in a little bit differently, just so they're a little bit easier to see. So this middle length one I'll make blue, and the short one I'll make green. So you can imagine if we were to make a triangle out of these three line segments, what would we have to do? Well, we'd have to join up the endpoints of each of these line segments so that it forms a triangle. So let's try to do that. So I'll start with the red one and the blue one. So here's the red one here. Roughly anyway, I don't need to have it perfect. And the blue one is somewhere around this length. And I'll just put it somewhere, say, here. And you can see there's no way I can take this little green line segment and have the endpoint of the green line segment join up with the endpoint of the red line segment. This red line segment is far too long to make a triangle. So I guess the answer to the question here is no, you can't. Here's an example where you can't. So a natural question to follow is, well, what's the restriction? So when can we do it? So when can we make a triangle? And I'll talk about it in a couple of different ways. So, first of all, you can kind of think of what's going on as taking two line segments, joining them up somehow, and then creating a third line segment to go between them. So let's stick with things roughly the length of the red one and the blue one. So I'm going to start with the red one down here. So there's my red one. And then the blue one, we'll have it here. Now, if we think about it, if I have the blue line segment so that the angle between the red line segment and the blue line segment here, this angle is very large, then the line segment that joins the endpoints here will also be very large. And the closer this is to a straight line, then the longer my green line segment will be. For example, if I rotate this even farther down, maybe I'll do this with a dotted line. There's my dotted line segment of the roughly the same length. Then the green line segment would be something like that, even longer. But there's, of course, a limit of how long this green line segment can be. So at its maximum, or near its maximum, we'll say, the red line segment, let's say that has length A, and the blue line segment that has length B, kind of the limit is when the angle here is as close to 180 degrees as possible. And then the limit on the length of the line that joins line segments A and B will be the sum of that. So at most, so the green line segment is at most A plus B. So the length of it is at most a plus b. And we can kind of look the other way. Let's try and make the green line segment as small as possible. So again, here's my red line segment. I'm going to say it has length a. And if I want to make this as small as possible, let's say it starts here. The green line segment would look something like this. But as I rotate this angle here towards the line segment A to make it as small as possible, let's say I rotate it here for now, then the green line segment gets shorter and shorter. And maybe you should pause the video and draw a couple of diagrams here and see if you can really get what's going on here. Or even better, maybe take a pen and a differently sized pen and treat them as the line segments A and B. And then you can visualize the length of a string or another pen or whatever that would have to join the endpoints of these guys. So try it out yourselves. And in the limiting case, how small can that line segment... Oh, I drew that too big. How small can that line segment in green be? Well, let's say I rotate this line segment B as close to line segment A as possible. So now it looks something like that. And then if I join the two endpoints that aren't joined up with anything yet, then the green line segment is near as short as it can be. So the limit it can be is, well, if B was right on top of A. And how long would this green line segment be here? Well, it would be the length of A minus B. So it's at least A minus B, where A is the longer of the two line segments. Maybe I'll write that here. A is longer of two. So on the next slide, let's write this up a little more formally. Okay, so here's our theorem that we just kind of talked about. If we have two sides of a triangle, and those two sides have length A and B, and if one is longer, let's say A is the longer one, then the third side has length C. And C has to be, this is interval notation, this is saying it's in the interval from A minus B to A plus B. And these round brackets mean not including those endpoints. Maybe I'll draw this on a number line just to make sure we get what's going on. So if this was a number line, and we had the point A minus B here, and then we had the point A plus B, here obviously A plus B is bigger than A minus B, then I'm saying that the length of C has to be somewhere in here. It can't be exactly A plus B. It can't be exactly A minus B, because then you have your other two sides lying directly either on top of each other or as a straight line, and that's not a triangle. But any other length in between them, you can make a triangle with. There's another phrasing to this as well. I like this one because it's a little bit easier to draw, but your other phrasing is as follows. It's called a triangle inequality. And it says, if a triangle has lengths A, B, and C, and I'll say where C is the longest side, so C is greater than or equal to A and greater than or equal to B, then the following holds. then the length of A plus B has to be greater than the length of C. So the sum of the lengths of the two shorter sides have to be longer than the length of the longest side. That's what this is saying. But both are saying the same things. This triangle inequality is just a rewording of the theorem we just talked about above. It's the same thing. And you might read in books as well, instead of specifying there's a largest side, they'll just say all of these hold. So you might see situations in books where this is crossed out and they just say, well, just check all of them. So A plus C has to be greater than B, and B plus C has to be greater than or equal to A. So you might see that as well. They all kind of mean the same thing. Let's do a couple of exercises to make sure we understand what's going on here. So here's our little exercise here. Suppose we know two lengths of the sides of the triangles are 4 and 7. And the first part wants us to figure out all possible lengths of the other side of our triangle. So maybe pause the video now, go back and look at the previous slide, and see if you can figure out this first part of the problem, and then we'll look at the second part. Okay, now that you're back, well, we know we can call this side here 7, we'll call it A since it's the longer one, and we'll call 4 B. So we know the other side, so the third side, let me write this in black actually, the third side must have length well, let's call it C, and it's somewhere in this interval. It's in the interval from A minus B, 7 minus 4, to 7 plus 4, which simplifies to, of course, it's in the interval from 7 minus 4 is 3, 7 plus 4 is 11. So if I was to draw this on the number line, here's 3, here's 11. The length of C of the other side that we don't have has to be somewhere between them. And just to be clear, so I'm going to do 7 in red and 4 in blue, kind of just like last time. So the situation where it's close to 3 looks like this. If we had our line segment of length 7 here, and the line segment of length 4, the blue one, is almost on top of our red line segment, and then the green line segment would be nearly on top as well in order to join up, and that would have length 3. So that is this situation. And the length 11 one, well, it's the opposite thing. It's when the angle between the 7 and 4 line segment lengths is as large as possible. So it's like something like this. It's near 180 degrees. This angle here is near 180 degrees. So we have length 7, we have length 4. So the green line segment that would match up with the two unmatched line segments to make a triangle would be as close to 11 as we could get. And again, it wouldn't be exactly 11. There's no way for that to happen because we need this angle to be just smaller than 180 degrees in order to make a triangle. If it equaled 180 degrees, it would be a straight line, and there's no way to connect the third side. Same here. If these line segments were directly on top of each other, this angle here would have measured 0 degrees. And then again, there's no way to join up the two unmatched line segments. So we need a little bit of an angle there. It needs to just be a hair above 0. It can be the smallest hair. And here it needs to be a hair below 180. Again, just the smallest hair. So this is the case when we're getting as close to 11 as possible. Okay, let's go on to the next slide, and let's try and classify when the triangle would be acute, right, or obtuse. All right, so our possible lengths are in this interval from 3 to 11, so I just marked it here. These are our possible lengths. And as a reminder, those Pythagorean inequalities, that is what's going to allow us to classify when a triangle is acute, right, or obtuse. Of course, a right angle triangle has a squared plus b squared equals c squared, where c is the longest side. And acute and obtuse have greater than and less than, respectively. And remember, in all of these, this c is the longest side. So maybe let's switch our notation here. So we have lengths 4, 7, and I used c in the last slide, but because c is standing for the longest side here, rather than calling it c, I'm going to call it, I don't know, L for length. So L, and L we know is in that interval from 3 to 11. So for all of these, we really have to compare the sum of the squares of the two other sides to the square of the longest side. And we don't know what L is. L could be anywhere from 3 to 11. It could be the longest side. It could not be. So we're going to have to break this up into cases. So let's do the case first where L is small. So 7 is our longest side. So case 1 is 7 is the longest side. So that's going to be our C in the Pythagorean inequalities. Okay, so then we need that, well, first of all, let me mark 7 in our diagram. That's going to be exactly halfway, of course. Okay, and so we're looking at this half of our diagram first. Okay, so we're comparing 4 squared plus the other side, L squared. Remember that L is not the longest side. We're saying 7 is the longest side. So we're comparing this. I'll use that symbol. This is either going to be an equals, a greater than, or a less than. I'm just putting a square there because it could be any of those right now. And we're comparing it to the longest side squared, so 7 squared. Okay, so this is 16 plus L squared. We're comparing, again, remember, it's either greater than, less than, or equal to 7 squared, which is 49. So let's subtract 16 from both sides of this potential inequality. And we get that L squared is being compared to 49 minus 16 is 33. So we'll take the square root of both sides since we're looking for the length of the sides and we're looking for L. So we get that we're comparing L to the square root of 33. And just as a quick note, we know that the square root of 25 is 5, and the square root of 36 is 6. So we know that the square root of 33 is somewhere between them, so probably somewhere around here. Square root 33. Okay, so it's between 5 and 6. So we'll put that in our diagram. So here is square root 33. And we know if this box, instead of having a box here, if we had an equals all the way down, that would be the Pythagorean theorem. if L equaled square root 33, imagine we had equals here for all of them, like that, then our triangle would be a right angle triangle. So I'm going to erase those again. Here we go. So exactly at square root 33, we have a right angle triangle. Okay? Now, if instead of looking at a right angle triangle, we looked at an acute triangle, well, that would mean that the two shorter sides here, the squares of them, would be larger than the square of the longest side. So if we put greater thans all the way down, like this, then we have when L is greater than square root 33, then it is an acute triangle. So again, I'm going to get rid of this, but you could imagine us doing the same calculation, just with greater thans all the way down. That's the acute test here. There we go. So I know that in this area here, which I'm going to draw in green, in this area, because remember, we're stopping at 7 because we're considering the case where 7 is the longest side, and if L is bigger than 7, then it's no longer the longest side. So here we have an acute triangle. So let's say if L was 6, for example, was length 6, or length 5.5, well, maybe not 5.5, but 6.5 for sure, then we would have an acute triangle. Okay? And if we had a less than all the way down here like this, then we'd be testing the acute Pythagorean inequality. And so if L is less than square root 33, then we have an obtuse triangle. Again, let me just erase this. So I'll do this in yellow. So between 3 and square root 33, we have an obtuse triangle. Okay, that's case 1. We did all the cases where 7 was the longest side. Okay, I'm going to erase this over here just to make a little room. Now we have to do the second case where L is the longest side. And of course, there's no case where 4 is the longest side because we already have a side of length 7. So let's do case 2. In fact, maybe I'll erase this as well to give me even more room. So let's do case 2. So in case 2, L is the longest side. So that means L has to be longer than 7. Well, it can't be any length longer than 7. It can't be longer than 11. Remember, the triangle inequality told us that the max length of that third side had to be 11. Okay, again, let's do the Pythagorean inequalities. Now L is the longest side, so we have 4 squared plus 7 squared, and we're comparing this to L squared. Well, we can simplify this. This is 16 plus 49. We're comparing this to L squared. 16 plus 49, you can check, is 65, which we're comparing to L squared. And now let's just take the square root of both sides. And we get that square root 65 we're comparing to L. And remember, 8 squared is 64. So square root 65, here's 8, here's say 9. This is square root 64. So square root 65 is just a tiny, tiny bit bigger than 8. We can't figure it out exactly unless we have a calculator, but that's fine. Just estimating where it is will help us. So square root 65, somewhere around here. Just bigger than 8. And we can play the same game. If we had an equal sign all the way down, then we'd be doing the Pythagorean Theorem. We'd be solving for that longest side. So when it's exactly square root 65, we have a right angle triangle. All right, if we were doing the acute Pythagorean inequality, we would have a greater than symbol, like I'm putting in now. And that tells me that when square root 65 is greater than L, or if L is less than square root 65, then we have an acute triangle. But remember, we're in case 2, where L is the longest side. So L can't be smaller than 7. So that is this area that I'm coloring in. Here, still, we have an acute triangle. And just like before, let me erase this. Imagine, I'll put my boxes back in. Imagine if we were testing the Pythagorean inequality for an obtuse triangle. And if we were, we would have less thans all the way down, because then the longest side would be very long. And in this case, when L is greater than square root 65, when it's bigger, then we would have an obtuse triangle. And that is this area here. But remember, we can't go past 11, since the triangle inequalities tell us that that side L has to be between 3 and 11. So here we know it would be an obtuse triangle. And that's a pattern that you'll see whenever you do problems like this, or whenever you're studying triangles. So you'll always have 2 situations where there'll be a right angle triangle. One when your unknown side is longest, one when the other longer side is longest. In between those, you'll have an acute triangle. And when the angle between 2 sides is very large, like over here, or very small, like over here, you're going to have an obtuse triangle. Let me see and draw a little bit of a diagram to kind of help us. So again, here's our length 7. And I'm going to start from the biggest case, so 11. So if we had something like this, here's our 4. If I had a situation like this, then the side L would be somewhere around 11. And as I rotate upwards here, then my third side, which would be attached here, gets smaller and smaller. But it's still an obtuse triangle, because this angle here is still very big. It's bigger than 90 degrees. And if I keep rotating this and rotating this, let me keep rotating it. And let me put some arrows in here so you know how I'm rotating it. As soon as I get here, here's my right triangle. So this is the situation where I have square root 65. So here's the situation where the length is square root 65. Okay, but I can keep rotating. So let me keep rotating. So as I keep rotating, you can see that now the angle between the line segment of length 4 and the line segment of length 7 is less than 90 degrees. And you can imagine if I joined these up now, this angle here is less than 90 degrees, but only slightly less than 90 degrees. look what happens when I move it just even a bit more, say somewhere around there. Then if I join up these here, I have a right angle triangle with the blue and the green side as the two legs of my right triangle. And that's a situation here where we have square root 33. And then maybe I'll draw another copy of this so it doesn't get too messy. Let me go over here. So we're somewhere around here so far. So there's it's not a perfect right angle, but you can imagine that that is a right angle. And as I rotate down even farther, what happens to the angle between the blue line segment and the green line segment? So now that gets very wide, and this gets very small. So remember, there has to be 180 degrees as the sum of all three angle measures. So as this one gets smaller, this one has to get bigger to compensate. So now we're over in this situation. When the length of the unknown line segment is small, then we have another obtuse triangle, because now this angle, the angle between the blue and the green line segment, is getting large. And if I keep going down, then the angle gets, of course, larger and larger. So here it's almost 180 degrees. So you can kind of see what's happening here. So the different lengths, as if you pick a length between 3 and 11 for the green line segment, then depending on how you pick it, you get either an obtuse triangle if it's kind of close to the extremes, a right angle triangle if the Pythagorean theorem is satisfied. Of course, just you have to check which is your longest side. Or if it's in between those, then you're going to have an acute triangle.